and then we will move on and start talking about polynomials. Real quick, before we start doing that though, if you could take a quick moment and take a look at your dress code situation. So if you are wearing outerwear, Vanessa, Walter, Ben, and you could rectify that for me before we get going too far, that would be splendid. Thank you. All right, so going through this from yesterday, I'm going to buzz through this kind of briefly and kind of explain some stuff as I go to recap some of the things I hoped that we remembered and kind of reviewed while working on this yesterday. So the first page is on factoring. There's really kind of three different approaches we can take to factoring something, depending on the form of the quadratic that we have in mind. So on number one, where the leading coefficient is 1 and I have both x's and x squareds, all I really need to do is find the two things that multiply to give me the last term and add to give me that middle term. Now, the things that multiply to give me negative 21, there's only 4 of them, and none of them add up to negative 5. So here we would just say not factorable. Now, we can confirm this. There's a test for factorability. I can also have done b squared minus 4ac. And if this is not a perfect square, that implies that we're not factorable. So in this case, negative 5 squared is 25. And 4 times 1 times 21 is 84. And 25 minus 84 is negative 61. And that's definitely not a perfect square. Perfect squares must be positive. And they're numbers like 1, 4, 9, 16, 25, 36, etc. That is like some number squared. So right away we could tell that's not factorable. Number 2 is possible to factor with a shortcut because we notice there's no x term. We have just x squareds and a constant. So here we'd be trying to use the difference of two squares factoring pattern, which is this. So if I can write x squared as something squared, well, that's x squared. And if I can write 81 as something squared, well, 81 squared is 9, then I should be able to factor this to just x minus 9 times x plus 9. Number 3 is the one where we're going to have to do the full factoring method because the leading coefficient isn't 1. So I'm going to begin by finding the two numbers that multiply to give me that leading coefficient times the constant term, so negative 90, and then add to give me that middle coefficient, which is 1. So those two numbers would have been positive 10 and negative 9. But that doesn't go straight to my answer. I need to use those two numbers to rewrite that x term as 10x plus negative 9x, or you could have written them in the other order. It doesn't really matter. And then we make two groups. We take a greatest common factor from the first group, so the number that goes into both 6 and 10 is 2. and the variable that goes into both x and x squared is x. So when I factor that 2x out, I have 3x plus 5. In the second group, the greatest common factor between -9 and -15 is -3. And then if I look at x and no x, well, there's no common factor there, so I just a -3. So when I factor that -3 out, I get positive 3x plus 5. And I notice then that if I compare these, they both have a 3x plus 5. So if I factor that out, I'm left with 2x minus 3. And there's my factored form, right? If you had checked to see if this was not factorable, which you might have tried to do, we'd have had 1 squared minus 4 times 6 times -15. Which I think comes out to be, what, like positive 361, which I think the square root of that is like 19 or something. So that does work. Is that right? I see Connor typing in his calculator there. Yeah, okay. Thank you. 4, similar situation, right? So we're looking for two numbers that are going to multiply to give me 25 times 13, which is 25, and add to give me -2. And you might have looked at that for a moment and gone, gee, it doesn't seem like there's two numbers that do that, but 325 is an awful big number. Maybe there's a lot of factors there, and I just didn't find the one that I needed. Well, in that case, if you start to believe that, hey, maybe this doesn't actually work, let's check to see if it's factorable. So if I do that b squared minus 4ac check, I get -900. Because it's negative, I know it's not a perfect square immediately. So I know this one is not factorable. You could have done that by exhaustion too, looking at every factor of 325. But if you get to it and you don't see it right away, I typically just do that check before I waste a bunch of time trying to enumerate every factor. So it tells me at least, like, do I need to do this and keep looking for something, or is it just done and I can move on with my life? You know what I mean? Okay. Here, again, this is in the form of it's a possible difference of two squares. So I'm going to try to rewrite 4x squared as something squared. That would be 2x squared. And 1 I can rewrite as 1 squared. So again, this is a difference of two squares. So I can write it like that. On to the solving page. So for a solving problem, again, you can solve 3 different techniques we would have talked about for solving. You can solve by factoring, you can solve directly, and you can solve using the quadratic formula. The only one of those 3 methods that's always viable is the quadratic formula. That's always going to work regardless of the form of your problem. The other 2, if the problem isn't factorable, you can't really use factoring. And if the problem contains both x's and x squareds, you can't really solve directly. However, if it is factorable, that's usually faster than the quadratic formula. And if there is only an x squared and not also an x, solving directly is usually faster than the quadratic formula, but marginally on those things. So if you just use the quadratic formula every time, that would have been fine. This one is the leading coefficient is 1. So if it's factorable, it's going to factor quickly and easily. So let's check that. So we need to find 2 numbers that multiply to give me the 24 and add to give me 10. Those 2 numbers are 6 and 4. And since the leading coefficient is 1, those take me straight to the factored form. I can shortcut through all that factor by grouping nonsense I had to do on the previous page. And if I apply then the zero product property, I can set each of those factors equal to 0 and then solve them both sides to get x equals -4. And subtract 6 from both sides to get x equals -6. Those would be the same 2 results if you use the quadratic formula also. You could not have solved this one directly, though. 7, I notice I have just x squareds. I don't also have an x variable. So this one is eligible to be solved directly. So when I say solve directly, I just mean like using the reverse order of operations. So like I'll subtract 9 from both sides, and then we'll square root both sides. So thing to keep in mind here when we square root both sides of an equation, that plus or minus. When we square root a fraction, we can do that rooting the numerator and then square rooting the denominator. The root of a negative, we have to use, creates an imaginary number, so that's going to give me I. So the square root of negative 9 is the square root of 9 with an I at the end of it. And then the square root of 4 is just 2. And that would be my answer there. Again, you could have used the quadratic formula there. It wouldn't have been, any really not much fast or not much slower, but it would have been maybe a little bit slower. The next one, again, I look at this. Maybe this is factorable, but that leading coefficient is not 1. So if it is factorable, I'd have to use the long factoring method, which at that point I think is no faster than just using the quadratic formula. So that's what I'm going to do in this case. This still might be factorable. In fact, I believe it was. But I'm going to just use the quadratic formula because I don't think it's appreciably slower to try to factor this. Okay, so negative of a negative is positive 27. If I typed in the square root of 27 squared minus 4 times 10 times negative 28, I think I get 43. If I type that into my calculator, that is. The thing that you'd have to be careful there when you type into the calculator is a lot of you guys, was not what I was supposed to do, would be tempted to drop the parenthesis around the negative 27 with the squared on the outside. Those that parenthesis needs to be there around the negative 27. And then the squared outside the parenthesis, or else your calculator is going to square first and then make it negative. It's not going to take the negative number and square it. So you have to be a little bit careful about that. The other option is just type it in as positive 27 there. Anyways, to get a final answer then, with the plus or minus, I'm going to do 27 plus 43, which is, what's that, 70? That reduces, or 3.5. And then 27 minus 43 is negative 16 over 20, which reduces down to... And since those are both rational answers, I know that this was factorable. So if you tried to do that by factoring and like that worked, that's cool. You could have certainly done that. I just chose to use the quadratic formula because the factoring was going to be, in my opinion, just as long as grinding through the quadratic formula. Presuming that it was even factorable. 9, the leading coefficient is 1. So if it's factorable, it should be easy to do. So I just need to find two numbers that multiply to give me 13 and add to give me negative 4. Well, there aren't two integers that do that. So I can't use factoring as my solving method, so I better use the quadratic formula then. So again, so 4 squared is 16. Minus 52 is negative 30. The square root of a negative creates an I, and the square root of 36 is just 6, so that's going to be 6i. And then to reduce this, I have to think about it as two separate for denominator of the whole thing. So that's going to reduce down to 2 plus or minus 3. Okay. And then our last one, come on, there we go. Same sort of situation, leading coefficient is 1, so maybe I can factor this. So multiplies to give me 1, adds to give me negative 3. Nope, that doesn't work. So better use the quadratic formula then. So negative 3 squared is 9. 4 times 1 times 1 is 4. 9 minus 4 is 5. And the square root of 5 can't be simplified any further. So this is as good as we can do. Okay? So the reason I started with this set of topics is today we're going to start talking about polynomials. A quadratic is a type of polynomial, right? And the idea here when we start factoring and solving polynomials is we want to continue to kind of break that big polynomial down into these smaller pieces, hopefully quadratic pieces that we already have a lot of tools to use to factor the quadratic pieces or solve the quadratic pieces. So eventually, really the focus for the second half of this unit on polynomials is going to be on factoring and solving. So the idea is you take some bigger polynomial, break it down into smaller pieces that you can handle using these factoring and solving techniques for quadratics or linear terms that we've done in pre-algebra classes or in the previous semester. Okay with that idea? So we'll circle back and still be using these techniques and these tools again later on in this chapter. But I'm going to drop this line of thought for today as we kind of build out what a polynomial is and how we can kind of add, subtract, multiply, and divide them. And that's going to be kind of the focus of today. And then next class we'll do a little bit more on division and start building out some factoring. And that's about where we had kind of left off with my class in semester 1. I think what we're starting today is new for Miss Morgan's semester, or for Miss Morgan's students. So we're just a couple days ahead. Yes, sir. Of course. Okay. So we're talking about polynomials here today. So we're going to start with just a bunch of definitions here to start, because there's a lot of vocabulary associated with this topic that is important that we understand, because I'm going to use it a lot to communicate ideas, and if we don't have the right language and we don't know the notation, it makes it more difficult to kind of understand what's going on. So we're just going to start with some kind of basic definitions. So a polynomial is the sum or difference of a finite number of monomials. And you probably hear that definition, you're like, okay, well, what the heck does monomial mean? If you don't know what that means, this definition doesn't really say a lot, right? So let's define what that is. Okay, so a monomial is the product of a finite amount of real numbers, boy, I butchered that, and a finite amount of variables. Okay. So what does that mean in practice? Something like 3x to the third is a monomial. because we could think about this as 3 times x times x times x. Everybody's okay with that? However, like 5 times x to the 1/2 is not a monomial. Because how would I rewrite that as a product of a real number and some monomial, or a variable? The 1/2 exponent is kind of getting in the way, right? So certainly the exponent on our variable needs to be a whole number. Everybody agree with that? Okay. What if we had negative 3x to the negative 5th? Is that a monomial? Still no, right? Because what the heck does a negative exponent mean? Well, doesn't mean multiplication, that's for darn sure, right? So I can't write that as just like negative 3 times a bunch of x's. So that can't be a monomial. What if I have 7 times the square root of x? That's a new operation, right? In the definition, we can only have multiplication going on. We can't have a square root. So again, not a monomial because of the square root going on in there. So in the end of the day, a monomial has to be like a real number and then a variable or variables, but the exponents on the variables must be positive whole numbers, right? So something like this, even though you have more than one variable, that's okay. They're all being multiplied, and all their exponents are positive whole numbers. So this is a monomial. And technically speaking, even something like this is a monomial. Even though we don't we're multiplying no variables, that's okay. Still going to count that as a monomial. Okay? Everybody feel okay about what a monomial is? If you understand that, then understanding what a polynomial is really easy because it's just going to be the sum or difference of a bunch of these things. So something like this is a polynomial because that piece is a monomial, that piece is a monomial, and that piece is a monomial. So the whole thing has to be a polynomial because it's just a bunch of monomials added or subtracted together. So this guy is not a polynomial. The first term is a monomial. The second term is a monomial. But that third piece is not a monomial because the exponent on that variable is negative. So it can't be a polynomial if all of its pieces are not monomials. Everybody okay with that? Okay. So hopefully we understand at this point reasonably well what a monomial and polynomial is. Now what we want to do is develop some vocab to describe the differences between them, right? So we've defined something and now we need a language about how to talk to it. Like what are the different attributes? What parts are important? We need to name some of these different parts for these things. Okay. So the degree of a polynomial is equal to the largest degree of each of the monomial terms or monomial pieces. Okay, well, how the heck do I find the degree of the monomials, right? That's the obvious next question. Let's define that then. Okay, so the degree of a monomial is just equal to the sum of the exponents on the variables. So if I have the monomial 3x to the fifth, the degree here is 5, right? The only variable is x. The exponent there is 5, so it's just 5. If I have the monomial negative 2x squared y to the third, the degree for this monomial is 5 again. The degree on x is 2. The degree on y is 3. 2 plus 3 is 5. How about 3x? What's the degree for that going to be? 1, right? Because remember, there's always an exponent of 1 there on the variable, even if we don't write it down. Very good. What about if we have just a number? We said that was a monomial still. The degree there is 0. If there's no variables, then the degree is just 0. Everybody feel okay about doing that? Okay. So to do a polynomial then, we'll look at the degree of each individual monomial. So the degree for the first monomial is 3, 5, 2, and then 0. So for the polynomial, the degree is then 5. Just the biggest degree of the monomials. So not the sum of the monomial degrees, just we're taking the biggest degree from the monomials. Everybody okay with that idea? Again, pretty easy to do, right? We're just looking at things and using a definition. It should be relatively easy. Again, we're not doing anything complicated right now. There's no computation. We're just kind of defining some things and talking about how to determine what those values are. And we're doing nothing more than just kind of looking at an equation or looking at a symbolic representation of something. Okay. Next piece is the leading coefficient. Let's try to turn that into a sentence. So we'll say the leading coefficient of a polynomial is the coefficient on the largest degree monomial So if I look at this polynomial, the degrees of each monomial is 2, 3, 5, and then 0. So this is my biggest degree monomial. So my leading coefficient is 10. So we just identify the monomial with the biggest degree, and the leading coefficient is the coefficient on that monomial. We're not talking about the biggest coefficient in the problem. It's the coefficient on the biggest degree monomial in the polynomial. Everybody's okay with that idea? Okay. Next up is another definition. So the constant term for a polynomial is just the monomial with no variable attached to it. So for example, 7x squared minus 110x plus 8, the constant term is 8. So for 6x to the 5th plus 10x to the 7th minus 7x plus 10x squared, what's the constant term here going to be? It's not 7, because 7 still has a variable attached to it. Constant term is 0, right? Because there's nothing on that polynomial that doesn't have a variable attached to it. But we can always write a plus 0 at the end. So the constant term is just 0 in that case. Everybody okay there? Okay. So we've talked about what a monomial is, what a polynomial is, what the degree of a monomial is, what the degree of a polynomial is, a leading coefficient, a constant term. What we need to do now is talk about like some naming conventions for polynomials. So one way we can name polynomials is by the degree. If the degree for the polynomial is 0, we call that a constant polynomial. If the degree is 1, we call it a linear polynomial. If the degree is 2, we call it quadratic. If the degree is 3, we call that cubic. If the degree is 4, we'll call that quartic. If the degree is bigger than 4, we're just going to name it by the degree. So we'll call it like a degree 6 polynomial. We'll just call it a degree 6 polynomial. There are special names for those, but they're like kind of esoteric and not really used commonly, so I wouldn't expect you to use anything really past cubic or quartic. I think 5 is quintic, right? I think if you have 5 babies at once, that's quints. I think it's the same prefix there. For those of you that like watching the TLC shows about people that have like an absurd number of children all at once. The other way we can name polynomials is by the number of monomial terms. Sometimes we leave out that word monomial there and just say the number of terms. So one term is just a monomial. Two terms we call a binomial. Three terms we call a trinomial. And really, if we have greater than three terms, it's just we say like whatever term polynomial. So if you had 6 terms, we just say it's a 6-term polynomial. Again, there's names for those things, but they're kind of not commonly used and not worth spending a bunch of time talking about. Like, these are the 3 that are pretty common. Any bigger than 3 terms, though, we would probably just name it by the number of terms. Okay. So just a little example. So let's say we have x to the 4th minus 7x squared plus 6x minus 2. So if we name this by degree, we'd say that this is quartic. And by the number of terms, we'd say it's a 4-term polynomial. Or we could combine these together and say this is a 4-term quartic polynomial and be a little bit more specific there and kind of use both. Is everybody okay with that idea? So if I talk about a quadratic trinomial, that'd be something that has x squareds, x's, and a constant, right? That's commonly the things that we were factoring last semester. We spent a lot of time talking about quadratic trinomials. Everybody's okay with that idea in terms of the naming? Again, just a little bit of vocabulary, nothing tricky to it. All you really are having to do is count things and remember some definitions, which is not so bad, at least for math class, right? Okay. I think that's good on the vocab. If I remember anything else that we need, we'll just kind of add it in as we go, but I think that does it for vocab. Next up, we're going to talk about operations. So the 4 operations that we'll talk about here are addition, subtraction, multiplication, and division. And I'm just going to kind of do some example problems inside of this because nothing here is tremendously complicated when it comes down to it. And I might show you a couple of different approaches at some of these, but we're just going to kind of do some example problems. Okay. So let's say my first polynomial here is 3x squared plus 7x plus 8, and I'm going to add it to the polynomial negative 3x to the 4th minus 2x squared plus 10. Is there any reason those parentheses need to be there in an addition problem? No, right? The only reason the parentheses would need to be there is if something has to get distributed, if there's some multiplication involved. But clearly that's not going on, so I can just kind of ignore them. So I can just kind of rearrange this any way I'd want. So basically what it comes down to is I'm just going to combine like terms. So how do I know if 2 of these monomial terms are like and could be combined? Their variable parts have to be identical. So in this particular problem, my like terms here would be, the 3x squared and the negative 2x squared, because their variable parts are identical. And the other pair of like terms would be the 8 and the 10. Since they have no variable parts, they are considered like terms as well. When we add two monomials together, we add their coefficients, but the variable part stays the same. So 3x squared plus negative 2x squared is just going to be 1x squared. And then the 7x doesn't have anything to combine with, so it's just going to stay the same. The 8 and the 10 give me 18, and the negative 3x, the fourth, doesn't have anything to combine with it, so that just stays the same. And typically, we like to write our polynomials so that their monomial terms are in descending order by degree. So we usually start with the biggest degree term first, and then the next biggest degree term, and so on and so forth. That's considered like the standard form for a polynomial. So that's all there is to it for addition, right? It just basically comes down to combining like terms. No big deal, right? Okay. So I'm going to do the exact same problem, but turn it into a subtraction problem. Now, you guys remember from like elementary school that subtraction is the same thing as like adding a negative, right? So that's really the way that I would think about this. Because it certainly does matter then the set of parentheses on that second polynomial. I have to make sure I distribute that negative through, right? If I have a negative sign in front of a set of parentheses, that negative has to get distributed through. Everybody's okay with that? Okay. So at that point then, after I distribute the negative through, I can drop all of my parentheses. And now it's just an addition problem where I'm combining. So again, my like terms here are the x squareds can combine and the constants can combine. Everything else, 3x to the 4 stayed the same. 3x squared and 2x squared becomes 5x squared. The 7x has nothing to combine with, it stays the same. And the 8 and negative 10 become negative 2. Again, I wrote down a lot of steps there. It's not really necessary to do all those steps, but I wanted to kind of explain what was going on there. Not unreasonable that you could still do that kind of a problem in your head if you wanted to, right? Not too complicated. But since it's the first time we're seeing it, I'm going to try to be really specific and explicit, not shortcut anything. Okay? Is multiplication. Actually. Okay, so let's say we're going to multiply these two polynomials together. Now, we've kind of done something that looks like this already last semester, right? When we had to FOIL out two binomials. Now, you could think about this the same way, where you can go, okay, I'm going to multiply this to this to this. And then multiply like this to this to this. And then multiply like this to this to this. And that's a perfectly reasonable way of doing it. It's going to get a little messy and a little long. And that's not my preferred way of doing it, but there's nothing wrong with doing it that way. What I prefer to do is kind of draw a grid. So what I'm going to do is I'm going to take one of the polynomials. I'm just going to use the first one and draw it as start making a grid for this. So I'm just going to take each term and put it in like a column like this. Now notice that I have an x squared term and I have a constant term, but I don't have any linear term, right? I don't have just a regular x. I'm going to include a spot where the regular x would go. I'm just going to call it 0x, which is still the same thing as 0, which is the same thing as nothing being there. And I'll explain to you why, and as we do the problem, why I'm going to do that, because it does make life a little bit more convenient if I do that. And I'm all about making my life easier because my life is hard enough. So now I'm going to take the other polynomial and basically turn that into rows. So I'm going to have the 9x squared, the negative 3, and then the positive 5. Everybody okay there? So now each box in this grid represents one little multiplication problem. So for example, this box that I've highlighted in yellow is going to be 3x cubed times 9x squared. So remember, when we multiply monomials, we multiply the coefficients together. So 3 times 9 is 27. And we multiply the variables together, but when we multiply variables, we add their exponents. So x squared times x to the third is x to the fifth. And if that doesn't make sense to you, remember that x squared is really x times x, and x cubed is really x times x times x. So x squared times x times x times x times x, which is x to the fifth, right? If you just go back and think about the definition of what an exponent means, it's obvious why we're adding the exponents when we're multiplying, but maybe not initially when you hear that. You're like, wait, what? So I'm going to go down and just fill in the rest of this here quickly. Oops. And here's where this big advantage of using this grid method comes in. So if I look at the columns here, and I look at the exponents, notice that the exponent is decreasing by 1 down each column. Right, the first column goes x to the fifth, x to the fourth, x to the third. If I look at each row, the exponent is decreasing by 1 as I go from left to right across each row. So the first row goes x to the fifth, then x to the fourth, then x to the third, then x squared. Everybody's noticed that? So it's hopefully easy to catch if you make a little mistake. And then in addition, finding our like terms is really easy because they're all going to line up on diagonals. So there's all my x to the fifths, and then all my x to the fourths, and all my x to the thirds, all my x squareds, my constants. Everything lines up on a nice, neat diagonal, so it's really easy to find our like terms to add together. If we did this the other way, where I just kind of foiled everything out, all my like terms would be all jumbled up in there, and it'd be kind of hard to locate some of them, especially if the polynomials were even longer. So I can now just add these things together. Oops. And there's my final answer. And that's my preferred method. It takes up maybe a little bit more space on your sheet of paper, but I think it makes it easier to diagnose if you've made a mistake and makes it easier to kind of keep track of everything, because oftentimes in a problem like that, just keeping track of all those different monomials is sometimes difficult, and it's easy to forget to multiply one of them to the other. Here, if we build the grid, like, you're not going to leave a box empty, right? It's harder to make a mistake there, which is why I prefer that. But you don't need to do it that way. Just the way I think is the best way to do it. Any questions about multiplication here? Okay. So the last topic here is the trickiest. So it's division. And I am going to remember, or to get us ready to do this polynomial division, I'm going to go back and review how to do like regular old long division that you would have done in like elementary or middle school, because it's the same basic idea. So let's say we wanted to do 1,247 divided by 24. Right? This looks like the kind of a problem you might have had to do in middle or late elementary school. So remember, we called these different parts of the division problem. We called this part the dividend. We called this part the divisor. And then we had an answer that was a quotient. And then we might have had some remainder left over. You guys kind of remember that from elementary/middle school? So the way we set this up is we took the divisor and we wrote it on the outside of our division bar. And we took the dividend and wrote it underneath. And then we just go digit by digit down the dividend to see if the divisor goes in. So does 24 go into 1? Nope. Okay, so then we go and consider the first two digits. Does 24 go into 12? Nope. So then we go and do the first three digits. Does 24 go into 124? Yes. And then we want to find the most times 24 can go into 124, which is 5. And then we'd write like a 5 here. And then we do 5 times 24. Which is, what, 96 plus 24, so 120. And then we'd subtract that down. And then bring down that last part that we haven't used yet. And say, okay, how many times does 24 go into 47? Well, that's a little bit easier, just one time there. 1 times 24 is 20. We subtract down, we get 23. So we'd call that remainder 23. You guys kind of remember doing that? Okay. So at the end of the day, we'd say our answer is 51 plus 23 plus 23 24ths, right? So the remainder over the divisor is giving you like the last little fraction at the end. Remember, a division problem is just going to turn your answer into like a mixed number. Everybody's okay with that? Okay. So let's do this with polynomials now. So let's say we have x squared plus 7x plus 6 divided by x plus 1. So we'll set it up the same way. So my divisor goes on the outside and my dividend goes underneath. Now, one way that this polynomial division works a little bit differently than the long division that we did with numbers is that when we do our polynomial division, all we care about is the first terms. So all I care about is how many times does x go into x squared? Or the other way to think about it is what times x gives me x squared, which is maybe the easier way to think about it. Because just x times x gives me x squared. Once I've decided that, then I multiply the x to the entire divisor, and I write my answer underneath and subtract down. Now, one of the most common places students make mistakes is making sure they distribute the negative across that entire polynomial. So usually when I'm doing this, I'm going to then immediately distribute the negative. Okay with that? So x squared minus x squared is 0. 7x minus x is 6x. And then I bring that last piece down. And then I'm going to repeat the second step. I'm going to say what times x gives me 6x? Well, the answer there is 6. That then multiplies to the entire divisor. I'm going to write that below and then subtract down. Everybody's okay so far? I'll distribute my negative, so that negative becomes negative 6x, and then negative 6. And 6x minus 6x is 0, and 6 minus 6 is 0. So my remainder is 0 then, right? So the answer to this problem is just x plus 6. Feel okay there? Let's do another example of that. So we have x to the fourth minus 3x cubed plus 7x plus 2 divided by x squared plus 2x minus 3. So there's one very important thing that's very different from this problem and the previous one. Now, obviously, the number of terms are different, right? But there's something going on with that dividend that happens in this problem that didn't happen in the previous one. That's really important. That we're missing an x squared term, right? That we go from x to the thirds to x's, but there's like a missing piece there. Everybody see that? So it's really important before you write down your problem that you look to see if you're missing any parts, because we need to make sure we include those or the problem gets a little bit funky, because stuff doesn't line up, and that often confuses the bejesus out of students. The easiest fix to that is just making sure you put the zeros in there if you're missing a piece. You guys see what I mean there? Okay. All right. So what times x squared gives me x to the fourth? Well, that's just x squared, right? So that distributes. So far, so good? Okay. And then we want to make sure we distribute through our negative. So negative of a positive is negative. Negative of a positive is negative. Negative of a negative is positive. So x to the fourth minus x to the fourth is 0. Negative 3x cubed minus 5x cubed is negative. So the answer is negative 5x cubed. 0x squared plus 3x squared is still 3x squared. And then I'll bring my last part down. And then I'm going to repeat. So I'm going to ask what times x squared gives me 5x cubed. And the answer would be negative 5x, right? So then I multiply this to all the parts. And then we subtract down. Before we do the subtracting, let's distribute that negative. So negative of a negative is positive. Negative of a negative is positive. Negative of a positive is negative. So negative 5x cubed plus 5x cubed is 0. 3x squared plus 10x squared is 13x squared. 7x minus 15x is negative 8x, and then we'll bring down our last part. And then we'll do one more time. I can tell I have just one more step left in this problem because the degree of x squared matches the degree of 13x squared. I know that'll be the last step when the degrees match like that. Anything left over at this step is just going to be a remainder. So what times x squared gives me 13x squared? Well, 13, of course. So I get 13 squared plus 26x. Hi, Miss Anderson.
At the end of the hour. At the end of the hour. At the end of the hour here. After Mr. Cole has wrapped things up.
All right, sounds good.
No problem. And we'll distribute our negative through. So negative of positive is negative. Negative of positive is negative. And negative of a negative is positive. So 13x squared minus 13x squared is 0. 8x minus 26x is negative 34x. And 2 plus 39 is 1. So all of that is going to be our remainder. So the way we'd write our answer then is that this is x squared minus 5x plus 13 plus negative 34x plus 41 over x squared plus 2x minus 3. Again, what we have here, I think I missed that, is quotient plus remainder over divisor. That's like the format for all of our answers here. How do we feel about this? Obviously, this is tricky, right? It's not trivial. This is brand new, and it's not easy. Hopefully, you have enough here that you'll feel okay going at it on the homework. If you get stuck on things, go back and look at the example. Go back and watch the video again, at least this section of it. There is one more thing that I want to do.